Okay, we're going to move forward now and talk more about vectors. This time we're going to talk about multiplying vectors. So we're going to multiply two vectors together in two different ways. So just as it stands, if you wanted to say, okay, let me take this vector p and I'm just going to multiply it by vector q, and that's going to be pq. That is not true, okay? This is not how vector multiplication works. You cannot do it this way. There's no way to do it this way, unfortunately. You have to pay attention to these two types of products. So you have a scalar product and you have a vector product. Both of them take in two vectors and they will give you different things. The scalar product is going to give you a scalar, a number. The vector product is going to give you a vector. So we're going to go over both of those really quick. Hopefully this will make a bunch of sense. And then you can use it in different ways to do different things. I'm not going to do the graphical part of this just yet. I might do it towards the end, but I just kind of want to get through the arithmetic of it so it can kind of start to sink in what we're doing here. So to start with, we're going to just talk about the dot product without doing the entire dot product formula, and then we'll add in the formula here in a second. So let's define a few vectors. So let's say I have vector A, and that one's going to equal 1, 1. And then I have vector B, which equals 2, 1. And then I have vector C, which equals maybe 3, 3. And let's do vector D equals -1 and -1. And we'll do one more, just vector E. And we'll make E equal -2, 1. Okay? So let's start by saying, okay, let's take the dot product, which is also the scalar product, of, let's start with A dot B. Okay, so that dot there denotes dot product. So what we're going to do here is it's going to look like this. You're going to take your two vectors, just write them next to each other first, put your big old dot there, and then 2, 1 is the other one. And so the dot product is pretty straightforward. We're going to take our x component and multiply it by our x component, and our y component multiply it by our y component. So we'll have something like 1 times 2, and then we'll have 1 times 1 in this case. And the only weird thing is that in between, we're going to add them. Okay, and so we'll get something, this will equal just some number. Or it might equal a formula if you have x's and y's, but that's something we can get into way later. So in this case, we got 1 times 2 plus 1 times 1, so that's just 2 plus 1, so we get 3. So the dot product of A dot B is 3. Okay, real quick, let's do the next one. Let's try C dot A. Okay, so in this one, we've got 3, 3 dot 1, 1. Right? And so this one's going to just be 3 times 1 plus 3 times 1. So that's 3 plus 3 is 6. These aren't too bad. Let's do one with some of these negatives. Let's just do, we'll do D dot B. See where that goes. So we've got -1 here and -1 here. And then we're going to dot that with 2, 1. Right? So in this one, we're going to get -1 times 2 plus -1 times 1. And that's going to equal -1 times 2 is -2. And then -1 times 1 is -1. So -2 plus -1 is just -3. Okay? So that's just the quick version of the dot product where all we're doing is worrying about just the two vectors. But there is actually a little bit more that goes behind the scenes of the full dot product. So what we're going to look at now is the expanded definition of the dot product. So this formula here looks essentially like this. We're going to have some vector u dot some vector v, and that equals, this double bar means magnitude. So you have magnitude of u times the magnitude of v, getting ahead of myself there, and then that's times cosine of theta. So what this kind of is starting to tell us, if we look a little closer at it, is that if I dot product two vectors together, that number I get is actually the magnitudes of both of those vectors times cosine of some angle. So we can actually solve this to tell us the angle between a vector. So we're going to pull these magnitudes over. So we're just going to divide everything by the magnitude of u and the magnitude of v. So we'll get u hat dot v hat. Now I know I haven't talked about the hats yet, so let's just really quick up here define what a u hat is. So we have something called a unit vector, which is defined as a vector divided by its magnitude. And then this really just means that this whole unit vector has magnitude of 1. Which I'll write down. Okay. And then we'll go into calculating magnitude during this lesson, so you don't have to worry if you don't already know what that is. If you do already know what it is, great. But we'll go into that during what we're talking about right now. Okay, so back to what we were doing here. So we have u hat dot v hat, since we divided them by their own magnitudes, and that equals cosine of theta, right? Now we're not quite to the point where this equals an angle yet, so we have to take all of this to the cosine inverse of each side. So we'll get cosine inverse of u hat dot v hat is equal to theta. So all of this comes from just this one formula here, right? So the dot product can tell us just some number that these two vectors multiplied together in this particular way are going to equal, but we can also reorganize it to tell us what the angle between those two vectors is, which that is really powerful for us. And this unlocks a few other types of vector manipulations we can do later. But for now, let's just look at what happens if we try some of these vectors that we already defined over here. So I'm just going to grab those, copy them, and pull them over. Okay. So, got a bunch of information here on the left, and we're going to hope that I can write at a reasonable size here on the right. So let's just start by saying we want to take the dot product of, let's do A and B to start with. Let me change color. Okay. So let's dot product A dot B, right? But in this case, I want to do it to where I find the theta between these. So I'm going to make sure I write over here magnitude of A, magnitude of B, and then cosine theta, and then we'll write our instruction, find theta. Okay? We could just jump straight to this problem here, but I just want to go through each step of this to make sure that we have an opportunity to do all the steps. So we'll start by doing the A dot B. So that's the part where you take your two vectors, which we've already done this exact combo, so this one I can go a little quicker through, I think. So we got 1, 1, and then 2, 1, which you can already see is just going to be 3, right? So now I know on this left side I have 3, and that's going to equal some stuff. So the next thing I need to do is I need to get the magnitude of A. Now to find the magnitude of a vector, you're going to take the square root of the sum of the squares of the components. So the components here, we have 1 and 1, so we're going to take 1 and 1, we're going to square both of them, and we're going to add them together. This comes from your Pythagoras theorem. So this is just normal Pythagorean theorem, which we'll actually go ahead and show that real quick, instead of just explaining it. So if I have, for example, this triangle here, and we'll pretend that I drew it perfectly to where those are both side 1, right? So right triangle. So we know by Pythagoras that this top side is 1 squared plus 1 squared. Well, if this is my vector, and this is my x component and my y component, now you can see why our magnitude of a vector is x squared plus y squared under a square root. That is the magnitude of whatever vector you are working for, right? It's just our hypotenuse, right? So that's where this magnitude formula comes from. So I'm going to just copy that and put it up here so we don't lose it, just in case. And then now we can just go solve this through real quick. 1 squared plus 1 squared is just going to be 2, so we've got square root of 2 for our magnitude of A. Okay, and then we can do our magnitude of B. going to be square root, and then b down here is 2 and 1, so we got 2 squared plus 1 squared. So 2 squared is 4, 1 squared is 1, so we got 4 plus 1 is going to be root 5, right? We don't need to worry about trying to use calculators and stuff to get exact numbers. That's going to be more than we're worried about right now, so we're just going to move on with these numbers. So what we can do now is we can just zoom in a little so we can squeeze this in here. So we got magnitude A, magnitude B, which we now just found are root 2 and root 5. And then that's all multiplied by cosine theta. So now we can just go ahead and write this so we know we're rewriting this whole equation. So I'm going to take 3 and I'm going to divide it by this multiplication of these two square roots. So I've got 3 divided by square root 2 times square root 5 is equal to cosine of theta. This particular one I did not think through ahead enough, so I don't think this is going to be pretty, but we'll still get some sort of answer. Now real quick, remember that when you have the multiplication of two square roots, you can multiply their insides and just leave them under the square root, which that is going back to exponential rules if you want to review that video on your own. So we're going to have here 3 over root 10, which we can also write as 3 root 10 over 10 if we normalize it. And so that's going to equal cosine of theta. And now all we have to do is our last little step here where we solve for theta by taking both sides to the inverse cosine. So inverse cosine of theta. The inverse cosine is by definition the inverse of cosine, so let's cancel, you just get theta. And then we have cosine inverse of 3 root 10 over 10. Now I would also say in this particular situation where we know we're going to put this into an inverse cosine, you may just leave it in this form here. We have 3 over root 10. That's fine because sometimes that'll give you a very obvious answer, especially if there's a weird angle that you're just familiar with. But most of the time you're going to want it in this normalized form because we're looking for something like root 3 over 2 or root 2 over 2 or 1 over 2. Those are the ones that we know really well. Positive and negative is fine. So in this case, we don't know this value just intrinsically off of our unit circle, so this would be something we would have to plug into the calculator to get some sort of value for. Root 10 is a little bigger than 3, so we've got 3 times something a little bigger than 3, so we're somewhere around 10. Bottom is 10, so this is somewhere around 1. So I would expect that this is somewhere between 30 degrees and 45 degrees if you put it into your calculator. Okay. So that's one we just did with the dot product. We'll go ahead and do one more example, and then we will move on to the cross product. I'm trying to zoom out. Here we go. Okay, let's see what happens if we take the dot product of A and D. I think this one's going to work out the way I want it to. So I'm just rewriting our formula with our new vectors in it, right? And so we know A is 1, 1, and D is negative 1, negative 1. So A is 1, comma 1, and D is negative 1, comma negative 1. And that's going to equal the magnitude. We already know the magnitude of A, right? We just found that a second ago, so we can just go ahead and skip straight to writing root 2 here. And then we can find the magnitude of D really fast. So we already know that's going to be the square root of negative 1 squared plus negative 1 squared, which, big surprise here, that's also going to be root 2. So then we have root 2 times root 2, and then our cosine theta as normal. Okay, so let's go ahead and expand this dot product out and solve it. So we get 1 times negative 1 plus 1 times negative 1, so we're going to get negative 2. And then over here, root 2 times root 2 is just going to be 2, and we're going to divide that over anyways. So we got negative 2 divided by 2 is equal to cosine of theta. Now, in this case, I think we actually are going to see that we know this number, right? So let's go ahead and do our inverse cosine situation. So the cosine negative 1, or sorry, the inverse cosine of negative 1 is equal to theta. Now that is a number we know. So if you think about your unit circle really quick, which I won't go into detail about how we get here because I have a video on that as well. So this is negative 1 comma 0 over here, and this is 1 comma 0 over here, right? Well, we know this is 90 degrees, or pi halves, and we know the whole thing is 360 degrees, or 2 pi. So half of that must be 180 degrees, or just pi. So we actually know in this case that theta is equal to pi. Now, let's think about that for a second. If the angle between these two vectors is 180 degrees, that tells us that they are exactly anti-parallel to each other, right? They're both on the same line, but they're in different directions. So that's called anti-parallel. So we can say, therefore, vector A and vector D are anti-parallel. Okay. Before we move on to the cross product, I actually do want to do one more example here of something else interesting you can do with the dot product. I think I've seen this a couple times for some of the students in the classes I tutor. So for this one, let's go ahead and just grab this vector e. So we're just going to say e, and it's equal to -2, 1. Now, what if I tell you that I have some vector that makes an angle of, we'll just say pi over 2 with, actually, sorry, let's not do pi over 2, I apologize. Let's say that we have some vector that makes an angle of pi over 4 with the vector e and the positive x-axis. Okay, so let's draw that out real quick to make sure we understand what we're doing here. So we've got just our regular coordinate system. Okay, and our vector e is -2, 1. So we're going to 2 backwards and 1 down. So it's here. We're going to go here. So that's e. And we know that the vector we want shoot. Okay, so we're going to look here for some vector that is going to be at an angle of pi over 4 with the vector e. And again, here our e vector is equal to -2, 1, which I've already graphed down here for us. So we're looking for, I guess I should declare the direction. So at an angle of pi over 4 with e in a counterclockwise direction. Okay, so that tells us we want to go this way, pi over 4. So I think we can figure out how to do this. So let's look at that formula again. So we have e dot, we're just going to say x is going to be our vector we don't know, and then we know that that's equal to the magnitude of e and the magnitude of x times cosine of theta, right? Now in this case we do know our theta. We have theta, so we'll be good there, but we don't know magnitude of x and we don't know this dot x. But maybe we remember that there was a second way to write this same formula where I had maybe e hat dot x hat is just equal to cosine of theta. So now instead of having 2 unknowns, I only have 1 unknown here, just this x hat. Okay, now you may say, well, we don't have e hat. But yeah, we do. We have, by definition, e hat is just going to be e over magnitude of e. That equals e hat, right? So let's go ahead and solve that out real quick. So we just need to figure out this magnitude of e, which we were going to have to do anyways. So we're not doing any extra work yet. Okay, so we know we have -2, 1, so we've got the square root of -2 squared plus 1 squared, which we already know is going to be √5. And so now we're just dividing e by that number. So we're going to have -2 divided by √5, and then that's going to be comma 1 over √5. And for right now, let's just leave it in this unnormalized form, okay? So the next step here, we've got to say, okay, well I have this vector e hat, and I'm trying to dot product that with this vector x hat, But this cosine of theta, if theta is pi fourths, we know what that is based on our unit circle. So that's going to be root 2 over 2. We just know that, right? We should have those down cold. And if you don't, just keep practicing. Check out the video I have on trigonometry. Now, this is kind of where it gets tricky. There's an instinct here to try and expand this dot product. It's something that works in certain situations. But in this case, that's really just not the right way to approach this guy. So instead, what we're going to do is we know if we multiply some scalar times some vector, maybe I shouldn't use the same letter, we get a scaled version of that vector. So why don't I, instead of trying to figure out how to expand this dot product and deal with the scalar, why don't we actually change this to say, well, the x hat is actually just going to equal root 2 over 2 times e hat, right? So I'm just going to scale my unit vector e, which has a magnitude of 1 now, but still gives me the direction of the vector e. I'm going to scale it by this root 2 over 2, and that's just going to equal my x hat. Well, let's give it a shot and see what happens. So we know we have root 2 over 2 still, and then over on this right side, we're going to rewrite our vector, which is negative 2 divided by root 5, comma 1 over root 5, right? And so now we can say x hat is equal to, just multiply. Remember, when we have a parenthesis, we're going to distribute, and that is the same as how it works for scalar multiplication of a vector. That's what we're doing here. So we get negative 2 root 2 over root 5 times 2. Oh, that looked bad, sorry. So we get 2 root 5. There's like a crack in my screen right there, and I think that's why it's acting weird down there. There we go, it's a little better. Okay, and then comma. Now we're going to do our same root 2 over 2 root 5. And honestly, you could simplify this, but why? Let's just stop here. This is correct. This is the answer to this question. We did exactly what they asked us to do. And now if we don't believe it, or if we want to check it, you could plug in to a calculator to get exactly what those values are. But 2 times root 2, that's going to be 2 times like 1.1 something. So that's going to be a little over 2. And then 2 times root 5. Root 5 should be like 2.3 or 2.4, something like that. So this is like something like 8. So this is going to be less than 1. And then over here, we're going to definitely have less than 1. So let's go over here and look. So if I have, so we're going to get something around here, more or less, when we do that to get our x hat. And that kind of makes sense, right? So we know normally pi over 4 is a 1/8 of a way around the circle. And so if we're here, an 1/8 of a way is, yeah, somewhere in the zone. So that makes sense. Okay, so now we've used the dot product in kind of a non-traditional way where we're given just a vector and an angle, and we have to find the other vector. Okay, now we're going to set up and talk about the dot product, or sorry, the cross product. So let's go, I'm going to copy these same vectors again.